Alright, in the Simon 10 help video, the one problem I didn't cover was question 22. This is a picture of the apparatus that we actually use in laboratory when we are in laboratory, and you can see, if you look at it, it's useful to be able to picture it. There are 4 rods that screw into a hub. The hub itself actually has several discs, so there's several places. It's hard to see in this picture, but in the other video I showed you an expanded version. It's hard to see that there are several places where you can wrap this. So if you wrap on a small inner one, it's not going to accelerate as much as if you wrap around the outside edge, and we'll learn about this next week when we talk about torque. But anyway, as this thing unwinds, the mass is going to fall slowly, but it's going to accelerate, and the wheel is going to spin with it. And the mass and the string will travel the same speed as the edge of the wheel, and as it accelerates, it'll accelerate with the same. So the tangential speed of the edge and the tangential acceleration of the edge will be that of the string and the mass. And we saw that in earlier problems. So that's one thing to keep in mind. The other is that we're going to talk about the way in which these things move. So if this spins, let's say it spins 3 radians per second. Let's just say it has a velocity of 3 radians per second. 3 radians is about a half a circle, right? A little bit less. Means it'll go a half a circle per second. This will go a half a circle per second. So you can see that the rotational quantities, whether it's the disk or the mass or the rods or the outer mass, the distance it travels, half a rotation, the speed at which it travels at any instant. Of course, if it's speeding up, the omega is not going to be constant, but the instantaneous, not delta omega, the omega at any instant will be the same for the inner and the outer and the rods, and the acceleration will be the same. But the distance this travels obviously is greater, and the distance that the outer one travels, or the tangential velocity of the outer one, is going to depend on the angle through which it turns times its radius of rotation, or more accurately said, the distance from the axis to the center of the object. And so this is where a lot of you got confused, because this distance here is 6 centimeters. And the rod is 32 centimeters. But if you read the description, the rod goes to the edge of the mass, like that. It goes right to the edge. It doesn't show it in the picture because it's inside. And so the distance to the edge is 6 centimeters. Then there's another 32 centimeters to the edge. But you want to measure to the center of this. So because this is 2 centimeters thick, you have to subtract 1 centimeter. So the R for the outer mass is going to be the 6 of the hub, right? Because it has a diameter of 12. The length of the rod minus half the width of that cylindrical mass, because we measure to the center. If an object isn't a point, we measure to the center of it. Since this one is already centered on the rod, then this one is 6 centimeters to the edge of the rod, right? That's 6 centimeters. And then the remaining distance is half the length of the rod. So you don't have to worry about the 1 inch here. You would just add half the length of the rod, which is 16. And so the distance that this is from the axis of rotation is 22 centimeters. Okay, I hope that helps. Anyway, let me give you a little help with some of the questions. So read over what the dimensions and times and distances are, and then think about that first question. How are you going to get the answer to the first question? So if you haven't done it, see if you can do it, and then I'll show you what I would do. So one way to get the answer to the first question is just to use the fact that the average omega equals omega final, right, plus omega initial divided by 2. If you take the final and the initial and divide by 2, you get the average. And since the initial is 0, that gives you the equation that the final velocity at the end is going to be twice the average. And the average is easy. It's just delta theta delta t. But you want to put it in radians, right? So we have 2.5 rotations. That's 2.5 times 2 pi, so that's 5 pi. Remember, pi is a number. That's the total displacement. 2.5 times 2 pi divided by the time, 4.77 seconds. That will give you the average. You have to double that, right? Don't confuse the average with the final. The average is just an average. The initial is 0, and the final is going to be double that average, at least in this case, because the acceleration is constant. Another way to get this, which is actually a better way, none of these questions do I ask you to get the acceleration, but you could get the angular acceleration by taking equation 3, go back and look at equation 3, group 2. There it is. This is an equation we use a lot. That's equation 3, group 2. And since omega initial, it starts from rest, is 0, you can easily get alpha by just doing the algebra. You get 2 delta theta over t squared. And so you can get the angular acceleration, which is constant throughout, right, by multiplying 2 times the delta theta. That's the 5 pi radians we just talked about. So it's altogether 10 pi divided by the 4.77 seconds, and you have to square it. And once you have the acceleration, then it would be easy to get this omega final, right? You would use equation 1 from the second group of equations where omega initial is 0, and you would just take that acceleration and multiply it by the time. And that, so you do want to get the acceleration. I'm not giving you the number, but I'll let you figure that out. Why? Because it will help you in getting a lot of the other quantities. Anyway, a lot of these are kind of trick questions. So the final maximum rotational speed of the apparatus is the same rotational speed as the outer masses. The final maximum rotational speed. And the linear, and the final maximum speed of the inner masses. So those are all the same, right? The angular quantity is the same, but the tangential quantities you will get, right? The Vt is going to be the omega times the r, and that's what we talked about earlier. If you want to get the two inner masses, you have to have r for the inner masses. And remember, r, it looks like a radius, but really it's the distance from the axis to the center of that rotating mass. And we did that. And the tangential speed of the outer masses, we have the radius for that. We use the same equation. The angular rotational speed of the two outer masses at 4 seconds, as opposed to 4.7 seconds, it's going to be less, and for that you should use the acceleration. So omega final is just going to be omega initial, which is 0, plus the acceleration times the time. That's equation 1, group 2, and now you have a time of 4 seconds rather than 4.77 seconds. And once you have the rotational speed, you can get the tangential, the tangential acceleration at 4 seconds. The acceleration, okay, you could get confused here. The alpha that we found that's not asked for, that's constant. And the tangential acceleration from the group 3 equations is just the angular acceleration times the r. So the angular acceleration is constant and the same for everything, but the tangential acceleration is going to depend on the radius, and it's asking for the outer masses. And so the 4 seconds here is irrelevant, really. The only thing, because this is constant, but the r is relevant. And the centripetal acceleration of the outer masses, see in your equations, you can use either vt, which you know, squared over r, or you can use the other form, omega squared times r. What's the r? The r is for the outer masses. And this acceleration does depend on the time. So you have to find vt for either vt or omega at 4 seconds, right? Because those quantities are not constant. They're changing. And they're going to be less. Well, we actually found it, right? The rotational speed of the two outer masses at 4 seconds. And so if you want to get the acceleration of the two outer masses at 4 seconds, you can just take that rotational speed, square it, and multiply it by the radius. So that would be the best equation to use for that one. And what's left? Anything left? 2 questions left, right? We didn't answer these. We just got the centripetal acceleration using omega squared r. So what's the angular acceleration of the two outer masses at 4 seconds? Angular acceleration? Trick question, right? 4 seconds? What's the answer? The angular acceleration was constant throughout. That didn't change. The other quantities change, but the angular acceleration stays the same. So you do need that quantity. You see that we calculated. It shows up several times. And since it's constant, it doesn't matter whether it's at the beginning at 4 seconds or at 4.77 seconds or any other time. Okay, that covers it all.